So when we're looking at bonds earlier in chapter 10, we were talking about bond polarity and that being the result of electronegativity differences. And if you remember back, when you look at a molecule like HCl, the chlorine is more electronegative than the hydrogen. So what that means is the electrons in the bond are drawn closer to the chlorine, and then what we end up having is a polar bond between the hydrogen and the chlorine, with the negative end being on the chlorine side and the positive side being on the hydrogen side. And we indicate our dipole moment by drawing an arrow and then putting a cross at one end to indicate the positive end. Or we could draw partial charges using the lowercase delta symbol, positive and negative. Now, we can also use something called an electrostatic potential map. And in the electrostatic potential map, I overlaid the H and the Cl, but this is the electron density map. And blue indicates positive charge, and this green represents neutral. There's a little bit of green in here. And then the reddish, yellowish tint begins to indicate more of a negative charge. So what we see in the molecule of HCl is we see a relatively more negative charge on one side of the molecule and a relatively more positive charge on the other side. So while the bond is polar, because there's only one bond in this structure, because there's a positive side on the molecule and a negative side on the molecule, it translates into a polar molecule because the bond is polar and there's no other bond sort of to compensate for that. But if we look at a molecule like carbon dioxide, what we find is that polar bonds don't always create polar molecules. So carbon is less electronegative than oxygen, but it has in carbon dioxide, there's a linear arrangement to the atoms. So we have dipoles for the bonds. That means the bonds are polar. But if you look at the molecule, you'll notice that the left side has a partial negative charge on it, and the right side has a partial negative charge on it. And when we're talking about molecular polarity, we're talking about a difference in polarity between the ends of the molecule and not the ends of the bond. So we do have partial positive here in the center. Actually, I should just draw it once for the carbon here, like this. We do have partial positive in the center. Because we have negatives at both ends, when the molecule is in solution, it appears to be the same charge one side or the other. And as a result, this molecule, even though the bonds are polar, the molecule is nonpolar. So this indicates something that's really important about molecular polarity, and it's the shape of the molecule. If there's a net charge on one side of the molecule, then it's a polar molecule. But even though it might have dipoles within the molecule, if those charges are distributed uniformly, and the molecule, and this is the important word, has symmetry with those charges, then what happens is the molecule is nonpolar. I often tell people a simple way to think about it, once you get good at visualizing the shape of the molecule, is to think of these as the bonds as rubber bands pulling on the central atom. And if in your mind you decide that the central atom doesn't move because the pulls are the same in all directions, then the molecule will be nonpolar. So here's another example. This is water, right? It's a bent molecule. Now, when we think about water, we know the OH bond is polar and the oxygen is pulling the electrons toward it. So, in essence, what happens is it's pulling the charge of both hydrogens, as is shown by the dipoles. It's pulling the charges of both hydrogens in the same direction. So where is the molecule's dipole, right? Well, looking at it like this, it's pretty easy to see. It's negative on this end and positive on this end. Now, another way to think about it, though, is just with this shape. Again, if these were rubber bands attached to the oxygen and you pulled it up like this and let go of it, right? It would oscillate in this direction. So that gives you the line which indicates the direction of the net dipole moment. That's what they're saying here. But then you have to use your brain and think, well, okay, this is the more electronegative atom, so this is the negative side on this side, and this is the positive side. And what you'll see is the molecule has a positive end over here and a negative end on here. So, a couple of quick rules for assigning polarity to molecules. One is if there are no polar bonds, the molecule is nonpolar. So you draw the Lewis structure. You look at the electronegativities of the atom or determine that they're very close together on the periodic table, right? And we can assume that some of those bonds are nonpolar. Now, if it does have polar bonds, then what you have to do, it says draw the shape of the molecule, but you have to be able to see the shape of the molecule in 3 dimensions. And if it says draw the vectors for the polar bonds, and if they don't cancel, the molecule is polar. But again, think of the rubber bands. The vectors are just the directions in which the polarities go. If they don't cancel, the molecule's polar. But you can also think about it as rubber bands. So, for example, if you have PtCl4, it's this shape, and the chlorines all have their lone pairs of electrons like this, and it's a square. It's square planar because there's a lone pair at the top and a lone pair at the bottom. Now you have to think about this shape. This shape, all these atoms are in the same plane. This pair of electrons above the plane and this pair of electrons below the plane. Now, if you think about these bonds, platinum is a metal, so has a very low electronegativity. Higher than the ones on the far left. So, but anyways, low electronegativity. Chlorine's got a high electronegativity. So you expect all these bonds to be polar. Now imagine that these are rubber bands, and they all have equal pull strength because they're all chlorines on the outside. Where does the platinum go when you let go of it? So you're holding it in the middle, and you have 4 rubber bands on it, right? Hopefully you've come up with the conclusion that the platinum would be suspended in between all 4, and that would be correct. That this is a non-polar molecule because there's no net movement in the charge. Now, you could also do what the book does. They draw the little arrows and think of vectors for the dipoles. For each one of these is pooling like this. And you have to decide, do those all evenly pull away from the center? And the answer is yes, but I've always found it's easier just to think of rubber bands pulling on a sphere and trying to decide whether or not what the sphere moves or not. If the sphere doesn't, if the central atom doesn't move, then the molecule will be nonpolar. So here's a good conceptual connection from your book. It's Conceptual Connection 11.7. It says, a molecule contains 3 identical polar bonds in a trigonal planar molecular geometry. Is the molecule polar? So what you have to do, and the answers are yes, no, and unable to determine, right, without more information. And the way you answer all of these questions, whether or not you're given the geometry and told what is connected to the central atom, or whether you have to draw it, is you always have to draw it out to look at it. And so we don't know what the atoms are, so we'll use the AX kind of notation the book uses. And it says 3 identical polar bonds, so I have a central atom A with, in a trigonal planar arrangement with groups like this. And apparently no lone pairs, and so the question, is it polar? And these are polar bonds, right? The AX bonds, because it says 3 identical polar bonds. So again, think of the rubber bands, right? Do the forces of the rubber bands or the vectors cancel? And the answer is determined by whether or not you think this will displace from where it is. Well, if it went this way, then it would be a polar molecule in this direction. If it went this way, it would be a polar molecule in this direction. And if it goes this way, it would be a polar molecule with the dipole pointing in this direction. Now, since these are all equivalent, we imagine that this doesn't move, and so what we determine is it's nonpolar, okay? Because the vectors cancel, or the rubber bands, the atoms in the center doesn't move. So when we were discussing polarity, it's important to remember the reason we're discussing it is because molecular polarity affects a lot of the properties of molecules. It affects things like boiling point, melting point, ability to dissolve other substances or to make solutions of other substances. It'll affect their viscosity, their surface tension, numbers of different properties. And many of these we'll go over in a chapter on states of materials. But right here, we'll just cover something very quickly. Polar molecules, like water, are really strongly attracted to other polar molecules. So it's kind of like a north-south magnet, right? Instead, it's a positive charge and a negative charge on the molecule. And as a result, they tend not to mix with things that are nonpolar, mostly because the nonpolar interactions can't stabilize this charge like other polar molecules can. So as a result, water tends to form solutions only with other polar molecules, and also tends to dissolve ionic compounds because of the charges that it has on it. So some molecules, right, will have parts that are polar and parts that are nonpolar as well, and it's actually the degree of polarity and the amount of nonpolarness of the molecule you have that determine how well things dissolve. Now, if you look at oil, oil is a nonpolar substance, which is less dense than water, and water is polar, and as a result, the two don't mix with each other. And so this is similar to like oil and vinegar salad dressings, where you have the oil, which is vegetable oil, and then vinegar is predominantly water and acetic acid, which is also polar. And as a result, they tend not to mix.